My name's Chris Walker.
My name's Dan Shine.
My name is Luke Cavallaro.
And I'm Josh Walker. Our client was BombTech Golf, and we are Project 21.
The problem that we were assigned was to make a shaft that was uniflex, which means that it would change its flexibility depending on how fast you swing it. While doing that, it also has to be light enough to be easily transported and swung while maintaining the durability, strength, and weather resistance of heavier golf clubs. Along with these requirements, it would also be required to be less than $17 to manufacture, or equal to it, and able to use by all ages, genders, and heights. And along with all of these requirements, it must be able to be compatible with driver, wood, and hybrid club heads and comply with all USGA rules and regulations.
This shaft will revolutionize the game. The average pro golfer needs many shafts for various distance shots. Our design allows for any distance shot, which requires various swing speeds, to be achieved with only one shaft. Because our shaft is being designed for the average golfer, however, they most likely will not know which stiffness he or she may need for their particular swing speed. Our design allows for any golfer to swing at any speed and achieve the best possible result. Design 1 consisted of breaking the shaft into 3 equal sections, L1, L2, and L3. L1 consisted of all hoop plies, which offer the most stiffness in flex. L2 consisted of all helical plies, which offer the most control by torque. And L3 consisted of all axial plies, which offer the most flex in tension. Design 2 proposed using a viscoelastic material, which when the club was swung faster, it would stiffen up, and when it was swung slower, it would flex more.
Design 3 proposed a change in the middle of the material to make it thinner.
Design 4 proposed a change in mass distribution, containing most of the mass at the butt and the tip of the shaft.
Due to the fact that Design 2, we're using the viscoelastic material, would be too heavy and too expensive, we in the end had to scrap it. Design 3, using the change in geometry, would be more likely to fail, which would be unsafe for the user, it'd be uncomfortable to use for the user, and it'd be really hard to manufacture. So we had to scrap that too. Design 4 would also, for the same reasons, not be useful because it'd be more likely to fail, uncomfortable, and hard to manufacture. However, Design 1 looked promising because it'd be comfortable, it uses the exact same material so it's not expensive, and it's light. So that's what we went with.
The final design is composed of 2 layers that take the bottom 1/3 of the shaft and break it into 4 sections of equal length. The upper 2/3 of the shaft in these layers consist of a hoop wrap, while the bottom 4 sections' fiber alignments decrease by 12.25 degrees until they reach 45-degree helical wraps at the tip. The 2 layers are wrapped in right and left-handed orientations in order to comply with USGA standards. This variation in fiber orientation should offer control over kick point location based on swing speed.
Our design is unique in many ways. Not only is the orientation of the fibers in our layers unique, but also the sectioning of the layers is different from other shafts on the market today. To verify that our design works, we used a finite element analysis program called Abacus. Once the shaft was built in Abacus, we applied a force on the shaft, which imposed a moment. This displaced the shaft 14 centimeters. We then applied the same force 5 inches away, which imposed a bigger moment, displacing the shaft 6.5 centimeters. Finally, we applied the same force 9 inches away, which imposed an even bigger moment, displacing the shaft 1.25 centimeters. These results are a proof of concept of our original hypothesis. To further prove our theory, we took a shaft containing helical plies and on one end epoxied a 2x4 with holes drilled at various increments to the tip. At the other end, a 2x4 was epoxied, which would soon be clamped down to a table. Masses were hung 1 inch, 5 inch, and 9 inches from the center, and their deflections were recorded. Our data again proved our theory. As the weight was moved outward, applying a larger torque, displacement decreased.
The task at hand was to create a universally flexible golf shaft. Over the past year, we worked alongside BombTech Golf, brainstorming and eventually arriving at a final design. This design was then tested using Abacus simulation software. The simulations proved our original theory of torque-dependent displacement. We then created a test plan which would be implemented in the event that a prototype of our design was later developed. We would like to extend a special thanks to Bombtech Golf, Professor Rand, and Dr. McInnes, without whom this would not have been possible.
Turn up the lights in here, baby.